Hi everyone, how's everything going in Ann Arbor? Are we all set? Or where's Sam?
Did you hear that? So we're gonna put a link in the chat for a new meeting. Where we're gonna do the neurosum. There it is. Yes, we're all joining this one.
All right. Okay. Just changing the link to the itinerary that maybe some teachers also want to join. Okay. Sam, are you set? Can I introduce you? I didn't hear anything. You were muted.
Yes, yeah, I'm totally ready.
Okay.
Whenever y'all are ready, I'm ready.
Very good. I think then we're all set. I'd like to introduce you Sam for our today's journal club about an accumulator model for spontaneous neural activity prior to self-initiated movement. He is studying neuroscience with a minor in math at Regis University. Is that pronounced correctly? Okay, and I think you'll finish this year. And we're all excited to listen to you talking about the paper. So stage is yours.
Awesome. Thank you everybody for being here. Would you mind muting that unless somebody comments? It's gonna be a little distracting. So could you mute your computer? Yeah, no, you're muted in Google Meet. Yeah, that's okay. So that's a little bit easier. And make sure you get someone's attention if you need to ask a question or something. It'll be a little bit hard to interact with the virtual audience. So the paper that I'm going to be talking about today is called an accumulator model for spontaneous neural activity prior to self-initiated movement. So first, I want to discuss a few things that are important to be aware of in reference to this paper. So the first one is something called a readiness potential. This is abbreviated with RP, and basically you can think of this as a pattern of neural activity which appears to precede voluntary movement. So just when you hear readiness potential or RP, neural activity that precedes voluntary movement, that's the connection you need to make. So next, I think an important thing to understand is what is the data that's being dealt with here. So we have EEG data that is being recorded for neural activity, and then the recording of actual movement times. So this is just to say that we are going to be able to extract when things happen based on EEG, but then we need to reference that to some ground truth, and that is the recording of the time onsets of actual movements. And then next, there's a little bit of a subtlety in the words they talk about threshold crossing times, and they also talk about waiting times. So these sound very similar because they are meant to be analogous terms, but when you hear threshold crossing time, make sure you think of a model. So that a threshold crossing time is like a waiting time for a model, not a waiting time for a human being. And when you hear the term wait time, that's referring to a human being doing the waiting. So a few other things. I'm sure some of you are familiar with this, but I just want to make sure we're all really clear on what I mean when I say the term time locking. So no matter what, in order to get some sort of understanding of time onsets, you're going to need to count time. And that's just with a timer. But eventually, especially in a task where you have recurrent events, what you can do is you can record exactly when each of those events happens, and then you can call those event onsets 0 time, and you can create a time scale that way. And that's referred to time locking. You're locking the time scale to the event. Okay. Then lastly, this paper specifically focuses on a task called a Livestream task. I'll get a little bit more into what exactly that is, but specifically there's an extension that this paper makes in terms of something called, that they refer to as the Livestream interruptus task or experiment. And basically when you hear that, just think of the original Livestream task with a little bit added onto it where there's an interruption happening. That interruption in this case is a sound that they refer to as a click. So first of all, I'm going to try and explain this paper through the figures. I really like the way Tim did that yesterday. It seemed really powerful. So first, let's talk about figure 1A. So what do we have here? Clearly, we have data related to some sort of EEG activity or something that's modeling EEG activity. This specifically, you're going to see a lot of figures that look very similar, but some of them are referring to actual data that was recorded from a person's EEG, and some of the data is actually from a model that is aiming to predict the way that the electrical activity should change over time. And the model that they use, they refer to it as a leaky accumulator model. But again, that's a little bit technical, and I'm not going to be able to explain exactly what that is except to explain the implications of that model. So in figure 1A, we're only looking at model data. There's no empirical data here. And what you're seeing, the first thing I want to address are the arrows at the top of the figure. Does anybody want to take a guess at what those arrows represent? Anybody online? Anybody in person? I'll give it 5 seconds.
That was, I'm probably wrong, back up. That was when the model moves.
Yeah, no, that's a slightly further extension of. So obviously the model isn't actually producing a movement, but they are. Yeah, so the movement that you're referring to, they would call that a threshold crossing event. So every one of those arrows represents a threshold crossing event, and you can see there are so many different traces there that have been superimposed on each other, but at each arrow there's one trace that has reached that top line, which is representing threshold in this case. So this is not time-locked data, but when we move on to B, we are looking at time-locked data. And so what that means is you're taking all of those arrows and you're lining them up one on top of the other and then comparing the traces in that way. So before I go on, does that make sense to everyone? Good.
Why is A not
When this lab started, so sometimes the habits are wait 15 seconds before it started moving, or sometimes it'll wait 1 or 2 seconds.
Yeah, exactly.
So it's time walking to the start of the trial.
And you'll notice that the arrows have a pretty high density, closer to about 2 to 3 seconds, and it's sort of like tapers off as you move out to the farther to the right. This is related to the fact that I'm not going to go too much into that right now, but just I want to draw attention to the fact that there's a higher density of those threshold crossing events at about 2 to 3 seconds that tapers off eventually. So now let's take a look at B. One of the main things that this paper was attempting to do was just to explain the distribution of waiting times. So on the x-axis you can see waiting times, and so as I was referring to with the arrows on the top of A, those waiting times have a distribution that's represented in this graph in B, and you can see that the wait times for the modeled data and the empirical data are very similar. So I bet this is getting a little bit confusing in terms of just understanding the task. So I want to just spend a moment to say what the task is. Is anybody familiar with the Livestream task? We've got Tim. Anybody? Chris? Okay. So the Livestream task is related to voluntary motion. So sometimes when you make a movement because you recognize a cue. That would be like somebody flashes a light and you try to move your hand as quickly as you can in response to that. That's not what's happening in this task. What's happening in this task is the participants are being given instructions to move spontaneously. So what exactly does that mean, to be told to move spontaneously? They're told that they need to wait at least 2 seconds, and then after that 2 second waiting period, they can, and this is not included in A, this would be happening before 0. So the trial isn't starting until they've waited that short period of time. And then after that, any time that they choose, they're allowed to move. It can be right away, it can be at the end, but the researchers ask them not to base their movements off of some sort of rhythmic pattern. They don't want them to count to these things. They want them to do it spontaneously. And the fascinating thing is that even though that's true, when we time lock to that event, we see a trend in the data beforehand that we can use to predict when a person is likely to move. And the time that a person is likely to move is represented in this mean wait time in B. So the most likely wait time is about 1 to the majority of them happen within half a second of 1 second elapsed from the 0 point. And in this case, the 0 point is the beginning of activity starting to move the accumulator closer to threshold. And I know that's a lot right now, but as we go through some of the later figures, I think some of those things will become a little bit more clear. So then going on to C, C is showing very much. Yeah, sure.
I was confused with B because it's the mean wait time is around 1 second after trial initiation. But then if you look at the data with the grayscale bars, it looks like it's 5 to 10 seconds. So I can't resolve the two graphs unless they're between this and this.
That I'm not entirely sure, but I think that might be including that 3 second wait time that happens before the participant is allowed to make that movement initially. And this in B, I think they're not including that 3 second wait time because that's the correct offset. But that wasn't incredibly clear to me. Does anybody else?
I think they just include the graph. Like B does like a smaller graph rate, and on the x-axis is 0, 5, 10, 15. And it looks like they just scaled it down 5 because like the graph gave you the actual time, but then this B graph is basically like normalized the x-axis to the 5 second mean. So at 1, you're at the mean time of 5 seconds.
Yeah.
At 2, you're at the double of that mean, which is 10 seconds.
No. So B shows you just the shape of the rising and falling event, and they're clipping it so you get 1 second before and 2 seconds after. But when that spike happens, that's what's given in the histogram.
So regardless, I think the important thing to recognize about this is that the model looks very similar to the empirical data, and that's one of the main goals of this project. It's tricky to claim whether or not we can ruin your free will with this experiment, but what we can say with some confidence is that this model of a leaky accumulator seems to be able to match the trend of empirical data. And again, that's the same thing that's being shown in C. It's just sign reversed. So the model, for some reason, they did in the positive direction. I think that's just because it's slightly more intuitive, but reaching threshold actually is a depolarization, so it's a decrease in voltage. So before I move on, does anybody want to add anything or ask any questions about these few figures?
No, that would be a hyperpolarization. Depolarization.
Yeah. Gotcha.
So from B, what we're supposed to take is just the shape of this spike is very similar. Yeah. Regardless of when it happens.
And yes, and specifically similar in shape to the wait times produced by empirical data and the distribution thereof. That makes sense. And so right now we're talking about wait times, but we'll also get into the individual traces for each. We'll talk about EEG activity instead of wait times in the later figures, if that makes sense. Everyone good? Yeah. Okay, and please interrupt if you have questions. Okay, so this figure was a little bit confusing to me because it attempted to draw a correlation using something called bounded integration, which I'm not entirely sure what bounded integration is. I think it's just a mathematical model that is used to model certain areas in the brain, and it tends to show this sort of relationship between averages and standard deviations. And so on the left here, we're looking at, in both A and B, we're looking at the wait times. In A, it's a simulated wait time, so they call it a threshold crossing time. And they're just saying that there's a linear relationship between the average and the standard deviation, or the mean and the standard deviation, that seems to validate this idea of a bounded integration model. But again, I didn't feel super comfortable to interact with that technical mathematical aspect. But I believe what they're attempting to do is relate spontaneous activity to the same models that are used in perception-based activity. And I think that bounded integration was something that has been used in perception-based activity. I don't know if anybody can comment on that, maybe shed some light on bounded integration or those other things.
Aren't they using, like, they're not using EEG data at all, right?
I think Etienne's unmuted. I don't know if he's trying to say something.
I think that this is no kind of like, they're just comparing the standard deviation of the wait time in general of the subjects when they are moving, and the mean waiting time for until they have this threshold crossing, right?
Mm. Yes.
And as in the figure before, like what I think that they're showing is just that they put their model the way that they can cover like all the variation that they also had in their experiments. So in general, the wait time over all their participants, that was the figure before, and this time they just want to show that they see a correlation in the like in the mean wait time in general to the standard deviation, and that they could also reproduce that with their model.
Yeah, I don't know that I can comment further on that, other than just to say that the model is producing data that seems very similar to the empirical wait times. So if nobody has any more comments, I think that figure 3 and 4 are a little bit more interesting. So here in figure 3, what we can see are, again, we're comparing a simulation and empirical data. But so this is now entering into that we're beginning to talk about the interruptus task. So before, when I was starting to describe the Libet task, it's this idea that you move spontaneously whenever you choose. But the researchers also wanted to see what would happen if you allowed a person to do that original Libet task, but then every once in a while you played a sound. They described it as a compulsory click. And what that means is it's a click sound that if you hear it, you have to press the button as fast as you can. What they're showing here are there's still Libet tasks, but there are no interruptions in this data. So what they're trying to show that the interruptus task should look very similar to the original Libet task if no interruption occurs. So you can see that the traces in the model look very similar when you have the classic and the interruptus task. I got to be honest, what it means to interrupt the model is a little bit confusing to me. I think that they do that mathematically, but I don't know. I think it's somewhat arbitrary because they talk about applying a ramp, and I think what that's saying is that they're almost forcing it to threshold. But again, I don't feel too confident to explain how they force interruption with the model. But I can say that in the empirical, but we are seeing with what they are claiming is an analogous model of interruption. They're showing here that these traces again look very similar. So any questions on that?
It seems strange to me if like you do this experiment, with Moors, and we're also with devices in the office, that the reaction time you just have to hit a light, or when you hit a button when you see a light or hear a sound is around 130 to 150 milliseconds.
Mhm.
How can it interrupt this when you just have to hit the button immediately? How can we be seeing activity and readiness potential up to 2 seconds before the
So there are on these graphs there are no interruptions actually happening. It's an interruptus task, but they only took when they do. Sorry, I wasn't clear about this. When they do the Libet interruptus task, they sometimes don't play the click before the person voluntarily chooses to move. So these are only including the data where they didn't have time to play the click before the person voluntarily did it.
Okay.
But there is something interesting about this. So you could imagine, so if you put yourself in the perspective of somebody doing this Libet interruptus task, you could imagine that every once in a while, if you had to voluntarily move, but every once in a while you were interrupted and you had to go really fast, you might kind of gamify it. And you might start to treat it like, oh, I wanna make sure that I get the fastest reaction time. And so people, the researchers claim that people tended to, because of that, have shorter wait times. So if you look at the smaller graph in B, you can see the red line and the gray line. So the gray line is what they predicted should be the wait time in the interruptus task, but it seems like the people skewed to having a shorter wait time and this is not with an interruption happening. This is the possibility of an interruption being there. And so the researchers kind of claim that the reason the red line has a peak slightly earlier than the gray, which is the prediction, is because the people are somewhat anticipating, and so they tend to respond voluntarily more quickly. So that's what I said from that. But I don't think they can really accurately or with credibility state why the participants were doing it. Just that it seems like when they do the interruptus task, empirically they are having a shorter wait time than predicted, or in the classical test. Go ahead. Oh, okay. Thanks. So Nora says, so the plot only shows the spontaneous movement in the task. Yes, that's correct. Even though the red line is the interruptus paradigm, those are only spontaneous movements. The person never was forced in these data from the interruptus task to move based on the click. Is that clear? Okay, good.
And then figure A.
Yeah.
I still actually see that text. Why does it say DT over 1,000?
I was not able to figure out what DT meant. The closest I get was, I think it was diffusion tensor possibly, but that was just the most reasonable of the things that I was able to Google.
I don't think it's an error.
It's definitely not damage total.
DT is just the difference of time, right?
Yeah, it looks like milliseconds.
Additional seconds.
Was Etienne going to comment? I thought I heard.
He was defining DT as difference of time.
Difference of time. Okay.
So it's milliseconds.
Could you say anything more on that? It's still, it's not super clear to me, and this was my paper. I don't know how clear it is to y'all then. Do you feel comfortable with understanding the X scale?
It's just time. Milliseconds.
Milliseconds?
Yeah, so milliseconds divided by 1,000 is seconds. So why they just?
Yeah,
it's like we're trying to be confusing.
Yeah, I'm not sure. It seemed like it would have been sufficient to say just milliseconds, but again, not. Yeah.
No, the DT is milliseconds. The x-axis in this case is seconds, right? And yeah, I mean they're just making it complicated. So easy.
I think the reason, so on B we see that the x-axis is definitely seconds, and on A it's time steps per 1,000. So I think because in A we're referring to the model, we can just think of it as there are sort of like the model has to render, and so like 1,000 renderings is, I guess, equal to 1 second in this case. But again, it still feels a little confusing. But I think we're safe to compare it to time. Do you want to add something, Sarah?
Oh yeah. I was just going to say that I think the reason that DT is used specifically for figure 3 is because it was previously referenced in figure 1, and they probably just for the sake of continuity wanted to continue that, even though it's kind of redundant with the over 1,000.
Gotcha. Okay, so I don't think there was a ton to take away from this, other than just again to see that the model seems to be matching up in some sense with the shape of the empirical data. That's the main, that's the claim to fame in this paper, at least the author seems to think so, that the data of the model is able to match the empirical data of a readiness potential. So now I figure 4 was a behemoth. It was 6 separate figures, but again, it was all focused on Libet tasks. And so I want to focus in on each of them individually. So I'm going to talk about A and B first, then C and D, and then I want to talk about A, B, C, and D together. So in both A and B, we're looking at some sort of time locking. But you'll notice that in B, the time locking leads to both the slow and the fast signals being lined up. So sorry, I guess I glossed over what those slow and those fast signals are. With the readiness, I'm going to go back to this just quickly. So with the readiness potential, actually, I think it'll be even easier to see on A. So looking at A, you can see this gray line moving through the data. And what that, I should have mentioned this before, but what that is an average of all of those traces. And what you'll notice is that none of the average never seems to cross threshold, but it does get closer and closer to threshold. And so, and it does so asymptotically. But what ends up happening is random noise in the, and so that getting closer and closer to threshold is the accumulation in the leaky accumulator model. And as it's accumulating to where it gets closer and closer to threshold, a random event, some noise, is more and more likely to cause a threshold crossing event. Is that clear? So if you think about it, let's say, what if at time 0 we played a click? Then you would still have to go from whatever is the, if I pay attention to the gray line, you have to go from a spot on that gray line all the way up to threshold. And you'll notice that that gray line, if you have to go farther, then you're more likely to have a slower response. And they tested that, and that's well, scatterbrains for struggle, but I believe they show that the reaction times are faster the closer the accumulator is to threshold. So when we go back to figure 4, when we talk about slow versus fast data in this sense, what we're really thinking about is, did the person have a slow reaction time due to the fact that they had not had much of the readiness potential accumulated? Or did they have a fast response because the accumulator had gotten them closer and closer to threshold by the time the click was played? Does that make sense? That was a lot of words. Anybody? Yeah, absolutely, absolutely. So in all of the data you're looking at right now, a click was played and a person was forced, or at least they were required to make a movement as fast as they could. In the slow case, the readiness potential hadn't been going on for very long, so the accumulation was much lower. And because the accumulation was much lower, it took more time to reach threshold. And as opposed to if you interrupt the readiness potential at a later stage, then there's a shorter barrier to overcome to get to threshold, so that tends to cause a faster response. And so what we are looking at now is from A to B, we're looking at, oh, sorry, go ahead. Yeah.
Was the difference between slow and fast? You're saying it's, the wait was longer for the fast? Or was it just, I thought it was...
So to say the wait was longer is ignoring the time locking paradigm slightly. So if you think about it in terms of a readiness potential, you don't know when the person is going to voluntarily begin that readiness potential, but once you know the readiness potential has begun, if you have the click happen earlier in the readiness potential, you'll expect a slower response. If the click happens later in the readiness potential, you should expect a faster response.
Okay, does it have to do with the random fluctuations, like on the readiness potential itself?
Well, you have to think, so before, the random fluctuations were the thing that was actually leading to threshold crossing.
Yeah.
But now in the clicking paradigm, you still have the accumulation, but it's not going to be a random threshold crossing. It's going to be an intentional threshold crossing. Does that make sense?
Okay. So But those fluctuations will still be present. Right?
They're still present, and so okay, I think you're talking about a boundary case. So what if they play a click right as you have a random threshold crossing event? Well, what the researchers did is they asked the participant if ever there was a click played right at the exact time that they voluntarily made the movement, then they were told to just say the word coincidence, and the researchers knew that that was not a reliable data point. So you see there's two mechanisms here for crossing threshold. There's random fluctuations, which seems to be the basis for spontaneous movement, and then there's also the possibility of actually endogenously attempting to make a movement, or not endogenously, sorry, using the cue of a click to then make a movement based on perception. Is that clear, that distinction? Good? Are we getting, can y'all gauge for the virtual world for me? Are we good? Okay. So the next thing I wanted to talk about is going to be a little bit more clear on the next figure, but first I want you to realize on B, the slow signal and the fast signal have been synced to the click. And this is, sorry. The 0 point is synced to the click. And I just want to be honest, it's confusing me as I'm saying this, so if I sound stupid while saying this, I apologize. But my understanding was that when they time lock to the click, the event of activity is something that we can align. So the problem that I'm running into as I'm saying this is that there should be a slow and a fast response to the click. So I may have to get some help if anybody wants to jump in. But basically what you'll see is that because those signals line up in B, they cancel out in the next figure. So I'll show you that and then I'll come back. You see how in D you don't see a massive, I guess that's a hyperpolarization. And in C you do see the massive hyperpolarization. And this is due to the fact that it's the difference in the time locking. So what we're looking at is fast minus slow. Let's just focus on B for a second. If you signal at about 2 seconds and you subtract the slow signal, you should expect them to cancel out. And so that's what you're seeing in D. But then let's go and look at A. So if you look about at the same time point, you see that the fast signal and the slow signal have very few points where they're actually equal. So they shouldn't be canceling out, and that's what we're seeing in C. And they related this to an auditory event-related potential in the sense that we know that the click is causing, I think that's what we're seeing here. So this dip in B, and I believe it's present in A, but it's a little bit more obvious in B. This dip, they were stating, I believe, that it's an auditory event-related potential. And when we time lock an auditory event-related potential because it has a very specific duration, has a very specific delay time, if we time lock to the sound, to the auditory event, then we should be able to see that cancel out. Does that make sense?
What are the
Whether it's fast or slow.
Dots above C and D?
So those are points of significant difference between the fast and the slow times. That makes sense.
With the fast versus slow.
Yeah. So let's try and bring it back to the framework. So we're interested in understanding this model of the Libet test. We want to understand voluntary movement, and specifically we want to understand it in terms of this model. So I think maybe going on to the third part, you'll see. Oh, sorry. This is basically what I was saying there, but we'll go back to that. I was quite confused by this figure a bit, except for the fact that so now this is the model doing the same the model in the same scenario. So E is related to that same movement time locking, like when the threshold crossing would happen. But that's confusing because what does it mean to cause the model to immediately be interrupted? You know, in some sense that's done artificially by the researchers themselves. So I found that somewhat confounding, but it does. But I believe that if you're willing to take on faith that the model and the interruptus model specifically was valid, then what you can see in these two figures is, again, similar to the empirical data. So they're just trying to show that their model is capable of producing similar data as an empirical study. And I believe it's related to an auditory event-related potential in this. But again, the model doesn't have ears. The model isn't listening. So whatever it means for the auditory event to cause a depolarization, that is in some sense arbitrary in this case. Or if it's not, I'm not really confident in why. And so that's why I included the legend here, just to see if somebody maybe could help us break this down. So I'll go ahead and read that. So the results of the simulation: time lock to threshold crossing, that's E, and time lock to interruption, F. A speeded response was simulated by introducing a steep linear ramp at the time of the random interruption. So again, that's what I was saying about how this model is, in some sense, it's difficult to understand what it would mean to cause an interruption to this model, because the model isn't actually listening. You have to actually introduce some random, or not random, but you have to introduce some specific type of activity into the model in order to represent an interruption. And they're describing that as a steep linear ramp. I'll go on, but if anybody wants to comment, please do. So, do we?
Basically, the point of this entire figure is to show that there's a natural ongoing spontaneous.
It's the natural ongoing spontaneous activity that you're referring to there. I think you're referring to the readiness potential in a sense. But the key here is that we want to establish a mathematical model that can mirror that readiness potential. And also we want to do the same thing in an interruptus task as well. But so that model then looks like the leaky accumulator, and then whenever there is a quote-unquote interruption, that is represented by imposing a steep linear ramp onto the model. If that makes sense.
I'm just wondering, from your research, it might have been in the supplemental stuff, and I wasn't sure if I found it. Did they give any explanation for how exactly they went about finding this specific, like, steep linear ramp that they applied to this circumstance?
I didn't see that actually, but that would be. I think honestly, it's due to the fact that they know that once you have been prompted to act, once you've been prompted to move, then there's no. It doesn't make sense that your threshold would go, or that your activity would go further away from threshold. I think they're basically using the intuition that once you've been prompted to move, you should only move closer to threshold, and they chose to do it in a linear fashion as opposed to a parabolic or an exponential fashion, which I don't know if we can necessarily say that's the correct mechanism. But yeah.
Yeah, of course. Is your mic up?
Oh, is it?
Here, yeah. No, I can just ask my question through my thing. Yeah, I think the application of a linear, skew here to attempt to, mimic that aggregation in a similar pattern is really interesting. I'm just wondering, in terms of applying that, it's really interesting that I couldn't see like a very distinct explanation for how they went about choosing this specific linear application.
Yeah.
I don't know, just interesting.
You're muted. You're muted, Stan.
Yeah, you're muted.
Samuel, you're muted.
Sam.
How about now? You okay? Okay. So what I was how far back should I go? 30 seconds, a minute, 2 minutes? Okay. So the main thing to understand about this paper is that our and this is a quote from the paper. So our model shows that a decision threshold applied to an autocorrelated noise, in this case the output of a leaky stochastic accumulator, can account for the specific shape of the readiness potential as well as the distribution of waiting times from subjects performing the Libet task. So again, this is an example of how we're gaining more of an understanding, but we're not necessarily able to make metaphysical claims. We can't necessarily say that the decision to move has been perfectly predicted by the readiness potential, because as you saw, there is a distribution of wait times. It's not prescriptive, but we are attempting to get closer to being able to predict how we do things like establish the time when we will make a spontaneous movement. If you really think about it, a spontaneous movement is something that doesn't really belong in a reductionistic paradigm, but because then there would be a spontaneous movement by definition has no way of predicting when it will occur. And so if we want to start to understand, well, do we ever? I mean, we feel like we make spontaneous movement. Raise your hands if you feel like you can move spontaneously. I just forced you to move, just kidding. But the idea is that we're, instead of necessarily being able to say a spontaneous movement is something that if there is a way that we can produce a spontaneous movement, there's a time course to it. And if we can start to understand what sort of mathematical models lead to the ability to predict that time course, then we can start to look for things inside of the brain which might have those same properties and lead to the same models that we see in empirical data, and start to give us a hold on what is the mechanism that seems to allow for spontaneous decision making. And if you think about it, the mechanism that allows for spontaneous decision making might be free will, or it might be the lack thereof. You know, so, any questions?
Yeah, I presented the Libet paper, many times. So I'm familiar with that paper. And to be honest, we've had 2 difficult papers 2 days in a row. And I was reading this last night, but I was probably really tired, so it was hard for me to really internalize the message of the paper. And I still don't really understand what you have thinking for me. Trying to explain it, like, why does it look so different from me?
Yeah.
So, is this paper important?
I think this paper is important, but almost very similar to kind of what we saw yesterday. I think that it begins with something that's honestly very profound, like this idea of a leaky accumulator model. I think that is the most valuable thing to take out of this paper. But I think then it goes on in some ways that are, I don't think they offer as much validity as just figure A, where we see a strong correlation between empirical data and the model.
Yeah, I think what we also have to take from the paper is that they have 2 kind of sets of also classifications right there. First of all, they're describing the behavior, then they're like doing a classification on the behavior of the subjects themselves, and then kind of taking means of 2 different sets that they were already predefining. So they had to choose between fast and slow. They had to kind of get an overview of the data first, and then they were kind of tweaking their model, I think, to predict the data the best. So this is kind of, I don't know, it's going for my sense of modeling a bit from the wrong direction, because I think they had the data first and then they were constructing their model to fit the data. And these classifications and how they were also separating their data points in the end was of course kind of they showed statistically that they're able to do it, that they have the right to do it, because there was a difference between the 2 groups. But at some point, it's still a bit arbitrary. And my question would be, how do you think could you kind of like tackle this problem that they were already separating the groups or the movements between the fast and the slow, and how can we kind of circumvent this problem. And can you please unmute again?
So just, I want to make sure I understand you probably. This paper is all about trying to make a model that matches onto empirical data, but we don't want the data to be the thing that is, I guess, tweaking the model. We want the model to itself predict the data. And you're saying, and it's true that they did tune their model so that it would be more predictive, but I want to push back slightly on what you're saying, because I think that there's also slightly the sense in which a linear model would have very little hope, parameters or not, of matching this data. So I think the valuable thing here is this idea that by producing a model which only has 3 parameters, in this case, they're able to match waiting times and EEG. So although I think that there is some sense in which it's arbitrary to distinguish the fast and the slow groups, and I don't actually think that the distinction between the fast and the slow groups is as pertinent for the applicability of the model. Does that make sense? Why the fast and slow groups aren't pertinent to the model?
Yeah, I mean, the insight also saying the fast responses to the unpredictable interruptions should be preceded by slow negative going voltage deflections, beginning well before the interruption itself, and even if the subject was not preparing to move at that particular moment. So I think for them it was also important to have this distinction between the fast and the slow, that they can actually show that it was for the kind of like the spontaneous movement and not the prepared one.
I think what you're saying is it's a little more clear to me now. So there's a sense in which there's a hypothesis to be made about the fast and the slow groups, and that we should expect that the readiness potential has accumulated closer to threshold when we have a fast response, and that when we have a slow response, it hasn't accumulated as close to threshold. Do you have a question, Sasha?
That's why I thought at first. Then reading the paper, look at the caption on figure 4, C. It says difference between fast and slow responses. The black asterisks at the top mark kind of we propose that the faster responses, top 33 percentile, were faster because ongoing spontaneous activity was closer to the threshold at the time of the interruption. So I think they mean by that not that the buildup was closer, but that the ongoing spontaneous activity, during that spontaneous activity, it was closer to the threshold than the slower group, which was during that spontaneous activity was farther away.
So I think you're right, but I think actually there's somewhere in the middle that we need. So in this idea of a leaky accumulator model, the spontaneous activity, it raises the average and it accumulates, but it so that spontaneous activity is leading to greater and greater likelihood of a threshold crossing.
So what's this slow group? What's happening in the slow group?
So in the slow group, that spontaneous activity is causing that average to accumulate up closer to threshold, right? And the slow group is before that accumulation has happened. So a random noise, that spontaneous activity that you're talking about, is less likely to cause an event. And the reason that should lead to a slow response is because it actually takes longer for you to change that voltage, you know? Is that a little bit more clear? But I think actually you did even raise a different confound in the sense that they decided the fast and slow groups based on the accumulator, when I think they should have decided the fast and slow groups based on their actual response times, and then gone back to check and see if they were at the correct point in the accumulation model. So maybe that's kind of to your point, Etienne, that they should have based the fast and slow groups on reaction times as opposed to where it was in the model, because that would have at least told us that that would have been able to validate or falsify the model. Anybody else want to add any questions? How did y'all feel about it?
On this base thing, two studies that I always have to face when someone does a debate experiment. There's another guy called Soon who.
Can someone unmute, please?
I'm just posting.
Yeah, I can unmute. Y'all can hear him now.
I'm just posting two articles in the chat that are relevant.
Perfect.
So they have a longer time course before decision. The readiness potential is so short that it's hard sometimes to know what we're measuring.
Mm-hmm.
But apparently they can go 4 seconds or 10 seconds before some sort of level.
They on average they tend to be about 2 seconds before the actual movement occurs, but like we talked about, there is a distribution. So like it's not like it's yeah, and again they talk about what we should believe about that. Does that mean that they're deciding 2 seconds before that they're going to make the movement? And really what they this paper goes on to discuss is that the spontaneous movement, they describe it as the commitment to move now, and they say that does not correlate with the 2 seconds before. What it correlates with is the actual threshold crossing, but as you see that readiness potential, you're getting more and more of a higher probability that you will have that threshold crossing event where you will commit to moving now.
Okay, so
and even if you think about it, if you had a statistically unlikely trial where you have a readiness potential, then maybe you don't have any threshold crossing events from the spontaneous noise. You have a significantly longer period of time before you have that final threshold crossing event.
Right. Yeah, it's like in the paper I posted in the chat. For the first, yeah. So in this one they claim to get a signal 10 seconds before.
That's what's expected of it? Oh no! Oh, you mean the other paper? Yeah.
Yeah, another paper. Yeah, it's crazy.
Very cool.
So what do y'all think? Is this important to you all? Does this affect you? Does this alter your perceptions of free will?
No,
Not really.
No.
Yeah, I don't think it does. Because it is cool though that certain like the fact that whether or not you will move or make a certain decision is based on whether or not a certain potential has crossed the threshold. I'm new to this idea, so I thought that was very cool. I had a question, but I think it's more of a technical question because I'm not that familiar with how they do time crossings. So how they realign the data somehow to, so it's more of a technical question. I kind of got the notion behind it, but I'm not sure how they get that time crossed figure. Does anyone have anything to say about this? Because it's a bit unclear to me.
Sam?
Sorry, I didn't mean to mute myself. Nora wants to know how they're getting the time crossing and the time of the crossing. But Nora, are you speaking about the model or the empirical data?
So I'm speaking about how, so for example, for the empirical data, how they decide, okay, so maybe if I go to a specific figure, it would be easier for me to ask my question. So, okay, let's say, yeah, so for example, in figure 4b, when they did the time locking, when they time locked the data, how they did the time locking with the click. I'm not sure what that means exactly, so I get the notion behind it, but technically how they accomplished that.
So you obviously have a clock running the whole time, so that you can get timestamps. But the participant in this task, they have a button, sorry, in their hand, and so it's kind of confusing that they use the word click as opposed to just sound, because you are actually clicking the button, and that is the movement and that's actually creating an annotation for that time step for that movement. But they also can time lock to the clicking sound. So they record in the experiment when the actual sound is played, and that's why we see that auditory event-related potential when we time lock to the click.
Okay. Yeah, that makes sense actually. Thank you.
Yep. Any other questions?
I just make the comment that this third author, Stanislas, I don't pronounce his name. Anybody know French? Dehaene. He actually is pretty well known for studying vision and consciousness. There's actually written some popular neuroscience books. But you can actually go to a bookstore and see.
Interesting.
And also, I posted on the chat. In 2005, there was a short story published in Nature by Ted Chiang. You might know Ted Chiang about the button that you like right before you're about to press it, it turns on. So it's like a 2-minute read. Really good story.
Interesting.
Ted Chiang. He's a computer scientist by day. He just happens to be one of the best short story science fiction writers in the world. He's on The Arrival, which was a movie he wrote.
Oh, I love that movie.
He was on the Very Bad Wizards podcast yesterday. Brilliant.
Very Bad Wizards.
Yeah, it's funny because it's like a lot of people like it. It's so talented. You know,
yeah.
Like way better. The movie looks good.
Well, if that's all, should we wrap up? Yeah. Thank you, everybody.
Thanks a lot.
Yeah. Awesome. Take care, everyone. Yeah.
Okay. That's